Okay, so thank you everyone for coming. Welcome to this term's final session of our category seminar at UNAM. Our speaker today is Kawahigashi from the University of Tokyo, who was nice enough to accept our invitation and who will be speaking to us about topological order and topological quantum field theory. The title of his talk is Topological Order, Operator Algebras, and Topological Quantum Field Theory. We will be reading questions from the chat during the talk. If at any point anyone wishes to be unmuted, please raise your hand and we will unmute you. There will be a questions round at the end of the talk, and we will be reading questions from our YouTube channel. So yeah, please, Professor, thank you very much.
Okay, thank you very much for the introduction. I'm very glad to give a talk here today. So today I'd like to talk about the application of operator algebras to study of two-dimensional topological order in connection to topological quantum field theory, which I'll explain. So physicists, particularly in condensed matter physics, they study something called the fusion categories, which I will explain, in connection to two-dimensional topological order. So we would like to clarify a relation between their approaches based on physics and our approach based on mathematics of operator algebras, and then we present the role of topological quantum field theory. So the outline of the talk is as follows. I start with something basic about group representations and operator algebras. Then I'll explain what a fusion category is. And then I introduce a notion of tensor networks. And I present recent work of Brutink and others published in 3 years ago. Then I'll explain what a topological quantum field theory is. And then I'll introduce something called an anyon algebra, that's a finite dimensional algebra, and its connection to a modular tensor category, that's some special type of a fusion category. Then finally, I'll introduce a PMPO, which stands for projector matrix product operator, and a higher relative commitance, which are notions in operator algebra. So the PMPO is a notion in physics, and the higher relative commitment are mathematical notion in operator algebra, and I'd like to connect them at the end. So I start with some rather classical idea about group representation and fusion categories. So we fix a group G, typically a compact or even finite, but anyway, some group G. And then we consider two irreducible representations, pi and sigma, of the same group G. Then we can make a tensor product representation of the same group G, pi tensor sigma. And then even if pi and sigma are irreducible, this tensor product representation is usually not irreducible. So we can make an irreducible decomposition of this tensor product. And that's a classical idea. And in particular, if the group is finite, then we have only finitely many irreducible representations up to unitary equivalence. And they are close in taking tensor products and irreducible decomposition. And also we have something called a contra gradient representation. This is a kind of a dual operation on representations. Then we have trivial representation and contra gradient representation, and they are somehow analogous to the identity element in the group and also the inverse element in the group. So we have a trivial representation, then this plays the role of the identity for the tensor product. So the pi tensor identity representation is unitarily equivalent to the original representation pi. So in this sense, this is really like the identity element for the multiplication. And also a contra gradient representation, this is often written as pi bar. This is kind of inverse representation, but the pi tensor pi tensor pi sigma this cannot be the identity representation because dimension, if pi has dimension d, pi bar also has dimension d, so the dimension of the tensor product is d squared, which is usually larger than 1. But this can be like this identity plus something more. And then this property basically characterizes the contra gradient representation. So in this sense, this pi bar is still a kind of inverse representation in this sense. So for finite group multiplication, we have the identity and the inverse elements. But for representations, we have something similar, so trivial representations and the contra gradient representations. Then, so finite dimensional unitary representations of a finite group, of one fixed finite group, they give a tensor category in the sense that we have a tensor product operation, we have irreducibility composition, and we have trivial representation, we have contra gradient representation. So in this sense, we have some product structure, so kind of multiplication procedure so this abstract characterization is called a tensor category. So it's something more general than a classical notion of a finite group. And this abstract axiomatization is called a fusion category. And this is, as a part of the axiom, we really have finiteness here. So we have only finitely many, something like reducible representations. So this finiteness is a part of the axiom for a fusion category. This name, fusion, comes from a notion in physics, which stands for some kind of tensor product operation. And yeah, so in this sense, we have something like finitely many, say, objects. This is a naming category theory. Then for two objects, we can make a tensor product and we can make an irreducible decomposition. So this is an abstract idea of a fusion category. Then, so this notion of a fusion category is really abstract and has a priori, it has nothing to do with operator algebras. But then we find some nice connection to operator algebras. So let M be a factor. This is a name of some kind of operator algebra. This is a certain simple operator algebra acting on the Hilbert space. So this is an algebra of bounded linear operators on a fixed Hilbert space, and it's closed under certain topology, and also it has to be closed in the star operation. Then, so this is some kind of algebra. So we have a natural notion of a representation theory of an algebra, somehow similar to a representation theory of a group. But this representation theory of this algebra is not much exciting, not very interesting thing happen here. But then the correct setting is the theory of bimodules. So for a representation of M, this is like a module. So module is some vector space on which this algebra acts. But then we have to consider a vector space, actually Hilbert space, with two actions of one algebra from the left and from the right. So we have to consider bimodule. That is an M bimodule. It means that we have a H, that's the Hilbert space. Then we have left and right action of the same algebra. So we have the left action of M, the right action of M. Then, so this is a natural notion of bimodule. And this really gives the correct notion of a representation theory. Then, for group representations, as I explained, we have a notion of a tensor product that plays an important role. But here, also we want to have a tensor product of bimodules. So if we have one bimodule H, MM bimodule, another bimodule K, we can make a tensor product over M. That's a kind of relative tensor product over M. So this is again M bimodule. So we also have an irreducible decomposition of this tensor product, and we have a notion of the the trivial representation that should be M itself as M bimodule. And also we have a contra gradient representation that is really H bar, that a conjugate Hilbert space. Then we have an abstract axiomatization of a fusion category, which is actually something called a unitary fusion category. And then, so we have an abstract setting of a unitary fusion category, but it turns out that any such a category can be always realized with bimodules of a certain factor m. So in this sense, operator algebras give a generic framework for abstract fusion category. So we can always realize a given fusion category with bimodules of operator algebra. Then I briefly mentioned connections to quantum groups because this is the most famous, most well-known idea to study this kind of fusion category. So a quantum group is a certain generalization of a classical Lie group. It's actually a Hopf algebra, which is a mathematical structure having a coproduct rather than the product. Then we have a natural notion of a representation of a quantum group. Then we have if we have two representations, we can make a tensor product using the coproduct structure. That's possible, quite natural. And so we have a tensor product and irreducible representation. So this is really like a group representation theory. Then we are often interested in examples arising from a one parameter deformation of a classical Lie group. So this parameter is often written as Q. And so we have a Q deformation of a classical Lie group like SUN and SON. Then it often happens that we have only finitely many irreducible representations when the deformation parameter is the root of unity. So Q to the power n is 1. If we have this kind of thing, we often have a finiteness of representations. In such a case, the representations of such a quantum group give a fusion category, actually something stronger, but we get a fusion category of representations. This finiteness of the number of irreducible representations is often called rationality because a certain parameter takes rational values. This is a well-studied notion. Then we have another important thing which is connected to fusion category. That's a conformal field theory. I only briefly mention this physics here, just for one page, but anyway. That's a two-dimensional quantum field theory with conformal symmetry. That's an infinite dimensional symmetry described with the Virasoro algebra. That's somehow infinite dimensional, yeah. Some question? Yeah.
Excuse me, so I'm a little bit confused. So when you say that when Q is the root of the unity, then there are only finite many irreducible representations, right?
Yeah, yeah.
But then if I consider Q just 1, then this should be a classical Lie.
Yeah, right. Q equal 1 is the exception. So when I say root of unity, 1 is excluded.
Okay. Thank you.
Sorry. Yeah, right. I'm talking about rather complex roots. Yeah. Okay. So then, so this Virasoro algebra is an infinite dimensional Lie algebra with some standard generators related to the diffeomorphism group of the circle. Then we have an operator algebraic description of a conformal field theory that's given by something called a conformal net. That's just a name in operator algebras, and which is actually a family of operator algebras generated by observables. Recall that in quantum mechanics, observables are represented with self-adjoint operators. So we have some lot of operators corresponding to lot of observables, and they generate algebras. And then they make a family of operator algebras called the conformal net. So we have a natural notion of a representation of a conformal net. That's fairly simple. Then we have a notion of a tensor product of representation. This is quite non-trivial, but this can be done. That was done almost 15 years ago in operator algebras and by Topological robots. Then we get the fusion category. Again, if we have some kind of finiteness, rationality. So this is like a compact group representation. So usually we get infinitely many representations, but under some particularly nice conditions, we get finiteness of irreducible representations, and many people are interested in such finite representation theory. And then we also have another algebraic system describing a conformal field theory that's called the Vertex operator algebra. That's another algebraic system which has been studied in connection to, say, the moonshine conjecture and other things. And this relation to conformal net has been studied recently. But that's all I would say about this theory. Then we have the main subject of this talk, that's the topological order and also anion. So a topological phase, this is an important subject in this talk. This is a homotopy equivalence class of gapped Hamiltonians, whatever. So that's basically some kind of self-adjoint operator acting on Hilbert space of the state in quantum mechanics. Then one topological phase has something called a topological order. And then we have finitely many quasi-particles. So this is a particular physical situation. Then we have finitely many kind of particles, sometimes called quasi-particles. And each quasi-particle is called an anion. This is something like a particle, but in a classical setting, we have notions of bosons and fermions. So two kinds of basic particles. But we have more general version of particles, and they are called anions. This name comes from any plus on. So such a system of anions is described with a fusion category with a non-degenerate braiding. So braiding means this kind of picture crossing. So we have some wire, and then we have two wires crossing one over, one under. And this kind of switching is called a braiding. So we have something like representing, we have pi here, we have sigma here. Then so this kind of switching corresponds to some passage from pi tensor sigma to sigma tensor pi. So this kind of switching is basically a notion of a braiding. And then if we have a nice braiding, then we say this fusion category is a modular tensor category. This name modular comes from the name group, modular group SL2Z. And then so this is the tensor category. So this is the tensor product operation is commutative in some interesting way. So in the group representation case, pi tensor sigma and sigma tensor pi are trivially unitarily equivalent. So nothing exciting happens there. And in the general fusion category, basically pi tensor sigma and sigma tensor pi could be entirely different. We have no relation. But in this situation, we have something more subtle. So pi tensor sigma and sigma tensor pi are unitarily equivalent, but in some non-trivial way. This is an idea of braiding. And this kind of system is expected to be useful for constructing a topological quantum computer. For example, Microsoft spends lots of money for this kind of research, and they hire many mathematicians. So they are led by Michael Friedman, a Fields medalist in topology. And so they want to create a topological quantum computer. So one anion corresponds to one irreducible object in the tensor category, modular tensor category. And this kind of modular tensor category also arises from a conformal field theory. This is my old work with Longo-Muger. Then I explain more graphical framework to handle this kind of question.
So excuse me again. So I suppose that here, when we talk about Hamiltonians, we should talk about many-body system Hamiltonians, right?
Yeah.
And may I ask, how do we describe the homotopy class here? Because I suppose they are gapped, but here I do not know how to describe.
Okay, that's more complicated. But roughly speaking, this gapped Hamiltonian is actually a sequence of Hamiltonians. And gapped means that we have some fixed gap between the lowest eigenvalue and the next value for all self-adjoint matrices. And homotopy equivalence means we have a one parameter deformation of gapped Hamiltonians, keeping a gap of Hamiltonian. This is basically an idea.
Okay, thank you.
Yeah, thank you. Okay, so the next topic is the tensor network. So this is some graphical expression to study vectors, matrices, and more general notions. So a vector Vj here. So here, for vector Vj has only one index, j. And for matrix Ajk, we have two indices, j and k. Then they are graphically represented as follows. So we have a circle labeled with V. Then we have one leg, one edge labeled with J. So this picture stands for Vj. So if we put label J here, this picture represents a number, the entry Vj. And also for a matrix, we put a circle with label A. Then we have two legs, two indices, so j and k. So this picture represents jk. And if we have more indices, we have some circles with 3 legs, 4 legs, and 5 legs, and so on. Actually, in this talk, we have something with 4 legs and 5 legs. And we are interested in this kind of thing. And they are generally called tensor. So this is just a name, a more general version of a vector of a matrix. Then the JL entry of the matrix product of AJK and BKL is given by this summation, of course, it's extremely elementary, summation of AJK, BKL over K. Then this is pictorially represented as follows and this way. So we have picture A, so A with 2 legs JK and B with 2 legs KL. Then the leg with this label K, this is in common for two pictures A and B. Then we join this edge and we put the label K. Then we have so this picture represents the product of A, J, K, and B, K, L. And actually we erase this label. Then here we have no label. It means that we have summation of all possible labeling. So this picture, we still have J and L. So this picture represents this number. So product of AJK, BKL, and summation over all K. So this is a concatenation of two pictures, and then we drop the label for the concatenated edge. And this kind of idea is called a contraction. So this is a picture of a contraction for matrix product. And also we can consider this kind of more general contraction of pictures, many more complicated. And we are interested in 3 legs, 4 legs, and also actually 5 legs. Then in this setting of tensor network, we have a recent paper of Bulting and other 6 authors. Ferestrate is the main guy, famous guy, senior guy. Their paper appeared in 2017, and they considered an algebra of matrix product operators, MPOs. This is a certain operator, actually just a matrix, finite dimensional matrix, arising from a system of physically nice tensor networks. So they put some assumptions on tensor networks, then they deal with tensor networks, and then they create a certain operator called a matrix product operator. And then they consider an algebra of these operators, and they are called matrix product operator algebra. So this is an algebra of matrix product operators. So we have some. So this is not an operator algebra in our sense. So this is written as MPOA. And then these authors consider the fusion category of matrix product operators. So we can multiply MPOs, and then we have a notion of a reducible decomposition of MPOs. So we have a fusion category of matrix product operators. Then they presented a graphical method to construct an interesting system of anyons. So they have contractions of more complicated concatenations, and then they worked on some algebraic manipulation of pictures. Then they introduced a new system of anyons, and then they have some physically nice arguments. then they show that they get a modular tensor category out of anyons and discuss its physical significance, physical meaning. And so this is really a physics paper. The paper was published in Annals of Physics, physics journal. And this paper is really physical, so they're not mathematical. They have no definitions, no theorems, no proofs. This is really a physics paper. But they are aware of similarity of their theory to an old work of Ognano in theory of operator algebra. So Ognano is a famous guy in operator algebra, and he had this kind of thing more than 20 years ago. And then, so this they recognize its similarity. Then we are going to clarify the role of operator algebra in this work and its further recent extensions. So we want to understand the role of operator algebra in a better way than this setting. Then for this understanding, we need idea of topological quantum field theory. So this is a name for general machinery to understand the topology of, say, three manifolds. And actually, this makes sense in any dimension, but we are interested in a three-dimensional case. So then we start with the fusion category. So we assume that we have some nice fusion category of, say, bimodules. Then we define notion of 6J symbols. This name comes from a classical representation theory. And this is an assignment of a complex number to a tetrahedron, like this picture. And then so we have a tetrahedron. Then we have 6 edges and 4 triangular surfaces. Then we label 6 edges with bimodule. So we put this H is bimodule. This is so this for this edge we put label H. For this edge we put K. For this edge we put L, and we also have 3 other remaining edges. We also put label there. Then we also label a surface with intertwiner. So for this triangle, okay, for this part, we have H, K, L. Then we make so we actually put also arrows here. So we have H tensor K here. So H tensor K. And then so this is an MM bimodule. And this is L is another MM bimodule. So we have a bimodule linear map from H tensor K to L. And so this is called intertwiner. So the intertwiner is something between bimodules. So this T, we put label T for this triangular surface. So we put one intertwiner here, another intertwiner for this triangle, another intertwiner for this triangle, another intertwiner there. So we have 4 intertwiners on 4 surfaces of a tetrahedron. Then for three-dimensional closed-oriented manifolds, okay, so then from this from these 4 intertwiners, we can compose these 4 intertwiners in some nice way. Then we get a complex number. So we get so from this picture we get a number, complex number, So this is an assignment of a complex number to each tetrahedron like this. Then for a three-dimensional closed-oriented manifold, we triangulate it. It means that we have lots of, but still finitely many tetrahedra for a fixed manifold. Then we label edges and surfaces with bimodule and intertwiners like this. Then for each tetrahedron, we have a number, and we have finitely many tetrahedra. Then we multiply these values. Then we still get the complex number. Then we add the values, add these complex numbers over all possible labeling. So then in this way, we have a summation of lots of complex numbers. So as a final result, we get a complex number. And it turns out that in this nice situation, up to some normalization, we get a complex number, which is a topological invariant of the original manifold. In order to show a topological invariance, we have to study how homeomorphic manifolds give different triangulation. But this kind of thing has been studied by topologists many years ago, almost 100 years ago. So we have a good understanding for them. Then, in this setting of three-dimensional topological quantum field theory, so if we have a three-dimensional, now if we are in dimension three-dimensional compact-oriented manifold with labeled boundary, we get a complex number in a similar way. Using this method, we can also define a Hilbert space, finite-dimensional Hilbert space for two-dimensional closed-oriented surface. Okay, so we get a number for a three-manifold. We get a Hilbert space for two-manifold. Then for three-dimensional compact-oriented manifold with incoming and outgoing boundary, so we have some picture. So this is dimension, one dimension less. But so here we have manifold M, and then this is a boundary dm. This is boundary dm. So we have two components. One is incoming, one is outgoing. Then so here for this boundary, we get the Hilbert space, and for this boundary, we also get the Hilbert space. Actually, the entire Hilbert space is a tensor product of these two. But anyway, we have two boundary components, and then we get two Hilbert spaces. Then this picture gives a linear map from this Hilbert space to the other Hilbert space. And then we have composition. So we have another manifold like this, M prime. And then, so we have a linear map for this manifold M prime. We have a linear map for this manifold M. Then if we concatenate the two manifolds, we get a new manifold, again with boundary. Then we get a composition of two linear maps that gives a linear map corresponding to this new manifold. That's an idea of topological quantum field theory. So for this kind of gluing, we have a composition of linear maps. Then for this particularly nice two-dimensional surface, just the two-dimensional torus, we have a particularly nice Hilbert space. So if the two-dimensional manifold is just a torus, S1 cross S1, we have for the two-dimensional torus, we have a special structure on the corresponding Hilbert space. So this is a finite dimensional Hilbert space. Then it turns out that we have a natural basis for this Hilbert space, and then tensor product among the basis vectors. And also we have a unitary representation of the modular group SL2Z on the Hilbert space. Then this gives a representation of the so-called S and T matrices. So this is like this kind of matrix. These two matrices are elements of SL2Z, and the image of these two matrices in the representation are called S and T matrices. Then this S matrix corresponds to a 90-degree rotation of the two-dimensional torus. So on the two-dimensional torus, we have a 90-degree rotation, and these entries, they give something called the Ferrari formula that's known in conformal field theory. Then we can identify this Hilbert space with the center of some natural finite dimensional fifth algebra, operator algebra, called the tube algebra of Ognano. This is a notion introduced by Ognano many years ago. Then the 90-degree rotation also makes sense in this setting. Then in this situation, we have a natural appearance of the braiding that's called the Drinfeld center in quantum group theory. So Knian has shown that we can create a new fusion category from this topological quantum field theory, and that this new category has a non-degenerate braiding. So original fusion category has no braiding in general, so no commutativity of the tensor product operation. But after passage to new tensor category based on topological quantum field theory, this commutativity of the tensor product emerges. So we get the modular tensor category. Then these S matrix entries have a natural interpretation in terms of the braiding, and for hop link is this kind of link. We have two circles intertwined in this way. This is a hop link. Then we have the Drinfeld center construction, which produces a modular tensor category from a fusion category. And Izumi clarified this construction and the role of the half braiding, this is a notion in fusion category, in the setting of the tube algebra and an operator algebraic construction called the long-Lorentz subfactor. Well, this name doesn't matter so much, but this is a notion in operator algebras. And this kind of construction was first given by Ognano in the name of the asymptotic inclusion. Again, this is just some name in operator algebras. But then so they are purely operator algebraic constructions involving infinite dimensional operator algebra, no topology, no no tensor categories. But it turns out that they produce operator algebraic realization of the Drinfeld center. This Drinfeld center is purely a categorical construction which first appeared in quantum group theory. Then we have 4 tensors, 6J symbols, and fusion category. Yeah. Then, so if we have, if we label 6 edges of tetrahedron like this one, so now we have, we have 6 edges, and we label these 6 edges with 6 bimodules from the fusion category, and we get a complex number corresponding to this tetrahedron. But then we fix 2 bimodules to be a certain generator of the fusion category. So in our setting, each fusion category has a kind of standard generator. I write HMM. This is the generator of the system. Then this is like a fundamental representation of in representation theory. So we start with the fundamental representation, and we make a tensor power and the reducible recomposition. Then we get all representations of a fixed group. So like SUN. So we get a complex number for each choice of 4 edges. So here we have 6 edges, but we fix this label H and this part H. So 2 out of 6 bimodules are fixed to be the generator. Then we have 4 A, B, C, D. So we have 4 more choices. And if we put A, B, C, D in some nice way, and also we put intertwiners for 4 triangular surfaces, then we get a number. Then we represent this number with this picture. So now, for 2 of 6 bimodules are fixed. So we drop the labels, them. And we have only 4 labels, 4 bimodules for the labeling. So we put A, B, C, D. Then we draw a square picture of like this. Then this picture are labeled with A, B, C, D, 4 bimodules for the vertices of the square. So this picture represents the number given by the 6J symbol on the left-hand side. Then this gives a 4 tensor. So this is a number, assignment of a number labeled with 4 edges. So in the tensor notation, we use this kind of thing. And actually, we don't put A, B, C, D, but we put edges here. So like A, B, C, D, and we put edges like this one. So instead of, so this edge is labeled with intertwiner. So here we have 4 surfaces, and these 4 surfaces correspond to 4 edges here and 4 labeling here for this 4 tensor. So in this way, we get the 4 tensor out of 6J symbols. And this is called, in the operator algebraic setting, this is called a flat connection. This is a name used in operator algebras. And this name, of course, originally in differential geometry, but this name comes from its discrete analogy to the notion of differential geometry. So in differential geometry, of course, manifolds are something continuous. But in this setting, we have some finite graphs, and they really behave like a manifold. So our graphs, finite graphs, are kind of discrete analogs of continuous manifolds. And in this setting, we also have a discrete analog of a flat connection in differential geometry. So we use the same name, flat connection, for this setting. So this is a nice special 4 tensor in our setting. So from out of 6J symbols and fusion categories, we get a 4 tensor that's called a flat connection. Then using this 4 tensor, we can produce a matrix product operator, just like in the paper of Brittink. So using such 4 tensors arising from a fusion category, that's flat connection. Then we can define a matrix product operator. And actually, this is a picture for MPO. And the projector matrix product operator, so PMPO as follows. So yeah, and actually for drawing this kind of picture, we have to fix the circle, and this can be any number. But in this picture, we put 4, this number, we have 4 crossing. And this crossing is really a 4 tensor. So in the previous picture, so now our 4 tensor, this 4 tensor is written like this. Somehow we have distinction between blue wires and red wire. So we have 2 kinds of wires. So this is a picture for 4 tensor. So here we have a circle, but circle is dropped in this picture. So we have this picture. This is this picture represents some projection in a finite dimensional matrix. And then we have some projection here, and we have a summation of A with a possible labeling for projection, only finite remaining. And here D of A is some kind of constant, kind of quantum dimension, and W is a certain fixed constant for this system. Then so just a normalization. So we have a summation of all possible projection with some normalization, and we make a summation. Then we have the same picture without labeling A. So this is a fixed labeling A. Here we have no label. And this picture represents a projector. And so this is a PMPO projection. Then the product structure of these MPOs is isomorphic to that of the relative tensor product of bimodules. So in this way, we get the fusion category of MPOs, but that's really isomorphic to the fusion category of bimodules. Then we have something called a zipper condition. This is some notion studied in condensed matter physics, but these MPOs, but they are really same as a fusion product, a tensor product of bimodules. Then in this way, they get an anion algebra. So Bulting and others, they introduced a new algebra, actually again a finite dimensional algebra. That's a new algebra called an anion algebra because they create kind of quasi particles called anion in this setting for a family of 4 tensors. So again, this is a family of flat connections arising from 6J symbols. Then they show that they get a modular tensor category, so with braiding, describing a topological order. So in this way, we get a new particle, a new system of anions where we have a braiding. And then they have some physical arguments to show braiding and the cell in the formula in this setting. And they work. So this is, they have some general theory, and also they work out examples are arising from a finite group with 3 cocycles. Sorry, this is cocycle, not cycle. So then they are aware of similarity to Okuniano's tube algebra in operator algebra. So their anion algebra is a typical element is represented by this picture. So they have some linear span of picture. So in this picture, so they have some 4 tensors here, 4 tensor, 4 tensor, 4 tensor. So we have 4 of 4 tensors, and we have this kind of box with 3 legs. This is a new kind of 3 tensor arising from the fusion product. So this is called something called zipper condition. So we have 2 zippers here, and we have 4 tensors. Then if we have 2 such elements, we can multiply these 2 elements just by composing and putting one picture to the inside. So here we have the inside here. So if we have some another picture similar to this one, we put this one to inside of this picture and we concatenate them. Then we get a new element. So this is the idea of a composition. Then in this way we get an algebra. And then we get this kind of abstract picture. This is a new picture with new 4 tensor. And in this way we get a new finite dimensional algebra. And that kind of analog of the Okuniano's tube algebra. Then we can really identify the 2 frameworks. So as I said, the paper of Brutink and others, they are really physical. So it's not clear what kind of things are mathematically really proved. But we can formulate everything in terms of operator algebra in a purely mathematically way. Then we can really mathematically prove what they want to have. So we get a family of flat connections for tensors from an operator algebraic consideration. Then we can next show that this family produces four tensors satisfying all the assumptions of Brutink and others. Then we can also prove that we may think that all four tensors in this setting arise in this way. If we have some operator algebraic fusion category, we can produce four tensors satisfying all the setting. But also, we may assume we can think that all four tensors they want to consider arise in this way. So our operator algebraic framework is completely generic. So then, in this way, we can realize all they want in this operator algebraic framework. Then, as long as they are, we are interested in fusion categories. So actually, so we can produce some four tensors which are different from what we have in operator algebra. But even if four tensors are different, the fusion category structures they have are really the same as ours. So usually we are not interested in four tensors themselves. We are interested in fusion categories they create. Then as long as we have this kind of interest, we can restrict everything to those arising from operator algebras. Then we can prove this theorem really mathematically. So the tube algebra of the fusion category in this operator algebra theory, and there are anyons. So this is our mathematical object in operator algebra. This is the anyon algebra in the physical setting of Brutink and arising from its flat connection. They are really mathematically isomorphic, the same thing. But isomorphic means that actually there is some slight difference between normalization constants. So we have some linear, rather trivial linear map involving some normalizing constant arising from quantum dimension, but they are quite minor. So up to this kind of small identification, we have two algebras that are isomorphic. Then in particular, the two resulting fusion rules are identical. So we have our fusion rule and they have their fusion rules, but they are really the same. And also the Ferrindi formula also holds in our setting because in our mathematical setting, this has been already proved. So just by passing our results to the setting, we get the Ferrindi formula in the setting. So they really don't prove this. And they just work out examples and they claim something general should be true. But actually, we can really mathematically prove that they are true. Then, yeah, okay. Do you have a question? Yeah.
Excuse me. So may I ask what kind of operator algebras are appearing here? So are they, for example, seesaw algebras or von Neumann algebras?
Actually, they are von Neumann algebras, yes. So-called
okay.
2-1 factors.
Okay, I see.
Okay. So then finally, I'll explain more connection to operator algebras. So we have a projector matrix product operator, PMPO, acts on some finite dimensional Hilbert space of actually certain states, including a projected entangled pair state, so-called PEPs. This is an important notion in condensed matter physics, and we have a state space of PEPs. And on this, our gapped Hamiltonian are supposed to act. So this is an important space of states, finite dimensional state. Yeah. Then the range of this projector matrix product operator. So this is a finite dimensional operator matrix, and the range of this projection is important. This is a space on which this PEPs lives. So then we can identify this Hilbert space with something called higher relative commutant in theory of operator algebra. So this is a notion in the theory of Jones in subfactor theory. So we have this notion. This has been studied by many people for more than 30 years. then so we can prove this theorem mathematically. So the range of projector matrix product operator, PMPO, actually we have to fix the length K, is naturally identified with the case, higher relative commutance in theory of operator algebra. Since an element in this range of the projection is identified with something called a flat field of strings. This is just a name in operator algebras. So this is a well-known object in theory of operator algebras for more than 30 years. Then we can identify their Hilbert space with our Hilbert space. So in this way, we get a nice mathematical understanding of the physical idea. Okay, so I stop here. Thank you very much.
Thank you very much for the very nice talk, Professor. Yeah, are there any questions or comments for Professor Kawahigashi?
Professor, I don't know if you could mention, I read that the theory of two factors produced the Jones polynomial. I don't know if you some words about this. And
okay. So from a sub-factor, we can create a fusion category and topological, three-dimensional topological quantum field theory. So today I explained how to get a topological quantum field theory from a fusion category of bimodules. But also we can create a three-dimensional topological quantum field theory using knots and links via Jones polynomial. So that's a different way produce the same three-dimensional topological quantum field theory. So in the case of the Jones polynomial, we get a topological invariant of a knot or of a link. But they can also produce a topological invariant of a three manifold through Den surgery. So this is a two different realization of the same topological invariant of three-dimensional manifolds.
Okay. Okay, thank you.
Are there any more questions or comments?
Yeah.
Yes, Roberto.
Hello. Thank you, Professor, for the talk. I wanted to ask you, maybe if we could go back a few slides when you were developing the example of the two torus, and you obtain a modular category. I think you mentioned how you get and how you interpret as well the S matrix as a rotation.
Yeah.
But why going beyond a braided category and getting a modular category? For instance, where does the T?
That's non-trivial. So we can show the construction of braiding is fairly simple, but we have to show non-degeneracy of the braiding. That's quite non-trivial. So one thing is based on topological consideration of this three-dimensional topological quantum field theory. And another thing is, another proof is really operator algebraic. So we have two different proofs based on different theories, but both are non-trivial, and I cannot give a simple answer to this question of why we have non-degeneracy.
Okay, and also maybe also impossible to answer quickly, but where is the T matrix coming from in this case?
In this case, so this is a twist of a torus. So we have two-dimensional torus, but we cut the torus, then we get this kind of tube. Okay, so then we twist this tube in this direction. 300, okay, 2 pi twist of this picture. That corresponds to the T matrix.
I see. Okay, thank you.
Thank you. Yeah. Does anyone else have any questions or comments? Yeah, I do have a question, if that's okay.
Mm-hmm.
Well, so in the construction of the flat connection, well, no, so when you get the flat connection from the 6J symbols, so when you usually define biunitary connections or flat connections from biunitary connections, you get a pair of graphs,
Mm-hmm.
which in the subfactor setting you get in the tower of relative commutants, you get the Bradley diagrams of the patterns and so on. So in this case, where do you get which are the graphs here, or are there any?
The principal graph of a subfactor produces for the flat connection. Yeah.
Okay.
Yeah. That's a more classical way to get this flat connection, but from today's perspective, I think it's better to use fusion category for this concept.
Okay. So there's I think I was only used to this way of constructing it through graphs and
right.
So this, okay. Thank you. So also, in the formula for getting the PMPO from the flat connection, you get your D of A, this number.
Yeah.
So can you actually interpret that as an actual quantum dimension or a dimension?
Yeah, that's right. Yeah, that's the quantum dimension of an object in the fusion category. Yeah.
Okay.
And if you look at the example arising quantum groups, that's really the ordinary quantum dimension.
Okay. Thank you. In the Anion algebra, so you mentioned Butnik and they constructed their Anion algebras for finite groups and 3 cocycles and so on, and they constructed their braiding. So what does the braiding look like in that case?
That's an ordinary quantum double of a finite group. That has been studied by people in Hopf algebra, finite groups quite well. Yeah.
Okay.
And in the setting of topological quantum field theory, that was studied by Dijkgraaf and Witten.
Okay. And I don't know if you could say a bit more about the, I think Yuan Shao already asked a bit about this, so a bit more of the operator algebraic situation under which you get the flat connection realizing the 4 tensors of.
So we take something called the hyperfinite 2-1 factor. For this particular operator algebra, we can realize everything quite naturally and uniformly.
Okay. And so the way you do this is through the relative commutant tower.
Yeah, that's right.
Okay.
So and then you look at the infinite, increasing sequence of finite dimensional algebra. Then at a certain limit, we get an infinite dimensional operator algebra.
Okay. I think that's all the questions that I have. Thank you very much. Are there any more questions or comments? I think I just want to make a quick comment. I don't want to interpret what Roberto asked more than maybe he can speak for himself. But I think he was just asked, if I understood the question correctly, the first question, I think you were asking about why you want, if you already have a braiding, why look for a non-degenerate braiding? Why look for more for modularity when you already have a braiding?
So if we have a braiding from the beginning, but possibly degenerate, through this procedure, we can create a new braiding with non-degeneracy.
Right.
And actually, it contains the original braiding as a subcategory. So it's a certain extension of the original system to a new, larger category with non-degenerate braiding.
Through the Dreifeld double construction. So I think that's something it's difficult to prove, but that you get, that you already have. It's not something you look for, but it's something you already have. Well, if there are no more questions or comments for Professor Kawahigashi, So, well, I'd like to say it was a really nice way of closing this term's sessions for the seminar. So yeah, it was great having you, Professor. It's a great talk, and we're very, very happy for having you.
Yeah.
Yeah, thank you.
Okay. Thank you.